Hello friends, welcome to GATE Academy Global. So today we are going to discuss one more important topic, that is stability of the systems. So as I can see, LS Manku, Yogita Verma, hello. So we are getting connected. Meanwhile, what we are going to discuss is, today the topic is stability, and we are focusing today the stability in time domain. See, there are different parameters on which you define stability of a system. So we will be seeing that how we can define the stability of the system if we are trying to analyze the stability by seeing the time domain of the system. That is, if you are going to take the impulse response either, or you are just going to take input in time domain and to predict output in time domain, you want to say that whether the system is stable or not. So as I can see here now, some more friends are getting connected. Anup, hello Anup. Shashir, hello. Vicky, Kunwar, hello. So what you see, we are going to discuss stability in very short, and you can say that in 5 to 10 minutes I am just going to discuss the basic concepts of stability, and then we will be solving questions on stability. We are just going to take basic questions and some words with which you are not, it may be possible that you are not familiar with. So we will be taking some examples, some MCQs on which you will be discussing on different words that are missing in your vocabulary in case of signals and systems. So are you ready? Should we start now? Sir, your lectures is on Monday and Thursday. Yes, there was something error in technical. So actually the link was not prepared at time. So we have not taken the schedule on Tuesday and Wednesday. But now we will be taking on regular basis, and you will be getting information regarding that live session. So we are just going to discuss stability in time domain. If you see, you will never going to find any of the GATE paper in which at least 5 marks was not there on the concept of stability. Either you discuss in control system or in network analysis, or either in signal system. There are so many subjects in which you are going to deal with stability of the system. So Anup, Telegram channel link, signals of system, you will be getting that in the description. You can get that link. So now if you see, if we are just defining the stability of the system, then before defining the stability, one thing that you know, that the total response of any system due to any input is combination of 2 types of responses, that is transient state response and steady state response. So one thing, that if you want to define stability of the system, then the system is said to be stable if transients of the system, transient response of the system die out and system can enter into its steady state. So if the transient state response vanishes with respect to time, then the system is said to be stable. And if the transient response is vanishing with time, then this relation is satisfied by taking the bounded input bounded output stability criteria. So whenever you are discussing other than in signals and system, then the systems that you will be taking will be LTI systems only, that is linear time invariant systems only. Therefore there you define stability based on transfer function or impulse response. So we are taking the basic stability definition comes from, if you say BIBO stability, then the first thing, that is BIBO stability criteria, says that if you are applying any input to any system, say it is your system, and if you are applying any input that is x of t which is bounded, and we have discussed what is bounded, but still we can take an example. So if this input x of t is going to be bounded, then the system is said to be stable only if the output y of t produced by this bounded input is also bounded. It must be bounded for every bounded input, that is there must not be a single bounded input for which the output is unbounded. And what this bounded word means, say you are applying the signal x of t as input, and if you say that the maximum magnitude of this signal that is attained by the signal x of t, say this maximum amplitude is anything, let it is bx, and if this bx, that is the maximum possible value of input signal x of t, if this bx is finite, that is if this b of x is less than infinity, then you say that this input applied is bounded. Similarly, if you want to say that this output is bounded or not, then if the maximum value attained by this output, say you are saying that maximum value of this output yt max, say it is yx, then if this yx is also less than infinity for this input which is bounded in time, then you say that the system is bounded input bounded output stable system. It is BIBO stable system. So we have discussed that if BIBO condition is satisfied, it means the transient part of the response is going to be vanished and you are only going to be left with the steady state response. That is your, you also know that the transient state response and steady state response can be compared with the solution of differential equation, as you are going to discuss, describe the system by differential equation or difference equation. So if you are solving a differential equation, then you will be getting two types of terms, that is complementary function and particular integral. So CF and PI also can be related with this transient and steady state responses. So now if you see what bounded input bounded output criteria is going to give you, first thing that the transients will be vanishing. Second thing, if you will be checking the impulse response. In control system, when you define stability in time domain, then you use the tools, that is Routh-Hurwitz criteria, impulse response technique, and the third is root locus technique. When you are discussing these three techniques to define stability of a system, it means you are analyzing the system, stability of the system in time domain. So impulse response technique that you have seen in control system, that defines that if a system is BIBO stable, then the impulse response, say h of t, is the impulse response of the system. Let it is impulse response, that is response of the system for impulse input. If this x of t is del t, then this y of t is known as impulse response. So if the system is stable, then limit t tends to infinity. Either we take plus infinity or minus infinity. Limit t tends to infinity, h of t must be 0. It means impulse response must be, if it is existing for infinite duration, then it must be a decaying function such that the value of impulse response is going to be 0 at t tends to plus or minus infinity. And the next thing is, this impulse response must be absolutely integrable. That is, it must be, if you talk about absolute integrability, then what we have seen that we must have to take care about, we are not defining area of the function h of t, we are going to define absolute integrability. So you will have to take integration from minus infinity to infinity. Instead of h of tau, you will be taking magnitude of h of tau d tau. And if this integral is giving you a finite value, that is, if this is finite, then you say that this system is, its impulse response is absolutely integrable. So the system is bounded input, bounded output, stable system. So it is the impulse response criteria that you are going to follow while you have to analyze stability of the system. So if we take some basic examples, to define BIBO stability, what the first thing is, you must have to take a bounded input. Then only you will be seeing that whether the output is bounded or not, but you will have to take a bounded input. And this, for this bounded input, what you can take either any finite value, or you can take step function ut. You know that ut is a function with respect to t. If you are defining this function to be ut, that is having value 1 from t greater than 0 to t tends to infinity, then it is a bounded function. At the maximum value taken by this function is 1, which is less than infinity. Therefore, this signal is, can be said as, told as bounded signal. So if you are going to take ut, u of t, or sin t, cos t, all of these functions which do not have any value for any instant of time, if the function is not infinite, then you say that these functions are bounded signals. So whenever you have to define stability, then you have to take any of the bounded signal, apply to the given relation and check whether the output is going to be bounded or not. Say we have a relation given as, and for bounded input, bounded output, what we have seen, first if we take yt is equals to xt, such if we say that there is a system for which output is directly equals to the input itself. So this system is definitely will be a bounded system, as if you are going to define for bounded input, if you are taking any bounded input, if this input is bounded, then as the output is input itself, therefore output will be bounded. It means that this system is BIBO stable system. If a system has output equals to input, that is, if a buffer system you are considering that is producing the output equals to input only but providing some delay, then this system is definitely a bounded input, bounded output stable system. Now what you must have to learn is, any operation is not going to remove this property of stability from this system. It means if you are taking a time reversal on this system, if you define y of t is equals to x of minus t, that is, you have taken time reversal, or you define y of t is equals to x of alpha t, that is, you are taking time scaling. If you define y of t is equals to x of t plus 4, that is, you are taking time shifting. If you are taking y of t is equals to a times x of t, or you take y of t is equals to minus of x of t. These operations are amplitude scaling and amplitude reversal. So what you must have to understand, that any of these operations, that is, if the system was earlierly stable, then if you are going to take any operation on this side, that is, if you are going to take either time reversal or time scaling or amplitude reversal, amplitude scaling, in all of these cases the system will be stable. System will again be stable, that is BIBO stable system. All of these systems are BIBO stable system. Some more things that you must have to understand is, if you are taking y of t is equals to x square of t, and if you have said that if x of t is bounded, it means it is never going to take value that is infinite. Then if all of the values in x of t is finite, then if you define yt maximum, that is maximum magnitude of yt, then it will be x of t maximum whole square. And if x of t is bounded, then this x of t maximum will be finite, then it will be finite. So if you are going to take square of a finite number, then it can be any large value, but it must be finite. It must be finite, therefore you again say that this system is again a stable system. What we have seen here, in impulse response stability, absolute integrability you have to check. See, we have one signal, that is, say h of t is given to be to you as signum of t. How this signum of t look like? It is a function that is having value +1 for t greater than 0 and -1 for t less than 0. It is with respect to t your function signum of t. So if you have committed a mistake and if you define the absolute integrability to be integration from -infinity to infinity h of tau d tau, then it will be simply integration from -infinity to infinity signum of tau d tau. That you are going to find the area under this function. As you are integrating any function, it means you are going to define area under this function, and if you don't have taken the mode value, if you don't have taken the mod, then this signum of t, area of this signum function, you know that area is 0, as the positive area is equals to its negative area, so the total area is equals to 0. So if you are not taking the mod, then you are getting what? It is equals to 0. So you will say that impulse response is absolutely integrable. But impulse response, absolute integrability do not gives the area of that function, but it gives area under the mod of x of t, h of t function. So if you see mod of signum of t, if you plot here mod of signum of t, then what will be this function? Mod of +1 is going to be +1 only, but mod of -1, this value will again give you +1. So now it is your function, that is signum of t, which can be said that it is a constant one. So if you are now going to integrate this function, then you are going to get infinity. So it will be, if you will be taking -infinity to infinity, magnitude of h of tau d tau, then this value is now infinity. So you must have to say that this system, it is bounded input, bounded output, not stable. It is not stable system. So we are now going to take some more examples on stable system, that if you have to define stability of the system. Say y of t is given to you as e to the power x of t. Now when this x of t is finite, that if all the values of x of t are finite, so if you are going to take any value in the powers of exponential, that is, you are going to define e to the power finite. So any e to the power finite value will always give you a value which will be finite. So if you are taking any bounded input, then the output is going to be finite. So this system is what? It is a stable system. Again, if you see, if we are taking y of t is equals to e to the power mod of x of t, then now see here, if this function, if you are going to take minus of mod of x of t, so either x of t is positive or x of t is negative, this mod of x of t is going to give you always the positive value. So what you are getting here, e to the power minus some finite value. As this value will be increasing, the value of overall this function e to the power minus finite, it is going to be decreasing. So you see here, either x of t is unbounded, that is, in this particular case, this system is always stable, that is, if you are going to take an unbounded input that is infinite, again you will be getting e to the power minus infinite, that is 0, that is, this system is never going to produce any infinite input, it is always going to be finite. So this is the particular system which is whose output is bounded even if the input is unbounded. Now, if you see some systems, like if we are going to define, we are just taking some easy examples just to revise your concepts of stability, because it is very important and you are definitely going to get some questions on it. So, if we take y of t, so one thing that you must have to take here, and do not have to confuse with that whenever you are applying a zero input, that is, if you are not going to apply any input, then you consider this 0 to be a finite value. That is, if you are not applying any input, in that condition also the output must be finite. So, if you are taking a system for which yt is equals to 1 upon xt, in such cases, if you see, if you are not going to apply any signal, that is, if you are going to apply 0 input, then this value will be 1 upon 0, that is equals to infinity. That if it is 0, then this value is what? Infinity. Other than, you can consider like this, that if you are going to take xt is equals to ut, then how you define ut is 1 for t greater than 0 and it is 0 for t less than 0. So, the y of t value will be 1 upon 1, that is 1 for t greater than 0, and 1 upon 0, that is equals to infinity for t less than 0. As the value of y of t is infinite, for any instant of time it can be, then you must have to say that this system is unstable. It is an unstable system. Again, if you see, if you have given a relation, that is, if y of n is given to you as ln of x of n, or you can consider it to be natural log, that is log base e x of n. So, if you have to define stability of the system, again what you can define here, that if you take x of n, then it will be given as e to the power y of n. Again, if you want to apply no input, that is, if you want to check if the input x of n is 0, then what should be the value of y of n? So, if x of n is 0, it means you have to get value 0 by substituting any value of y of n. So, e to the power what value will give you 0? It means y of n, it is only one possible value, that is y of n must be minus infinity. Only in this case the output e to the power y of n will be 0. It means you are applying input 0 and getting output y equals to minus infinity, which is not finite. Therefore, again this system is not stable. Whenever your denominator is going to be 0, then the system is going to be unstable. That is, if you have given y of t is equals to e to the power x of t minus 4 upon t minus 8. If you see in the numerator, then if this x of t is finite, if you are taking this x of t to be bounded, then we have seen that x of t minus 4 will also be a bounded input only. So, if e to the power finite, this will be finite for every value of x of t, but you have taken t minus 8 in the denominator. So, at t is equals to 8 seconds, say at t is equals to 8 seconds, this x of t minus 4 is having a value, say we are taking this value to be, at t is equals to 8, it will be x of 4, t minus 4, that is x of 4, let x of 4 is defined to be 5. So, this value at t is equals to y of t, at t is equals to 8 seconds, if you see, then this value is 5, and 8 minus 8 you will be getting 0. So, the value of output will be infinite. So, we are applying input, that is 5. So, e to the power 5 it will be e to the power 5, but this value is finite, divided by this 0, the result is infinite. It means again this system is an unstable system. So, you can have several examples. So, whatever examples we have taken, we are just solving them, the relation of output and input given, we are solving in that relation in time domain to find stability. If you have to find stability in frequency domain, then we will be using Laplace transform or Z transform. Individually we will be discussing that, but if you have to define, there can be two cases. If you have to define stability in time domain, then there are two cases. Stability, case 1 is you are dealing with a LTI system. First case, the system is LTI, and the second case, it can be a non-LTI system. So, if the system is LTI, it means it can definitely have impulse response, so that you can find out the transfer function. So, if the LTI system is given to you and say there is any differential equation is given to you, then what you have to say, we are checking this in case of continuous time system first. We are checking this in case of continuous time system first. So, if the system is LTI system and if it is described by a differential equation, so what you have to do is, step 1, take Laplace. take Laplace on the given relation of output and input and find out the ratio of output upon input. That is, in second step, you have to define transfer function that is given as h of s, which is the ratio of y of s to input x of s, under the condition when the system is initially relaxed. So you just have to take Laplace transform in the given relation either or in the given differential equation. Then you must have to find out this ratio that is going to be y of s upon x of s. So when you have obtained this h of s, then the third step will be find its inverse Laplace transform, and the inverse Laplace transform of this transfer function will give you impulse response, that is h of t. And when you obtain this h of t, in the next step use the condition to define stability, that is whether this h of t is having 0 value at t is equals to plus or minus infinity or not, whether this h of t is absolutely integrable or not. So you first have to take Laplace transform, then define this ratio, that is transfer function, then take its inverse Laplace, that is your impulse response, then apply the conditions of stability on this impulse response to define stability in time domain. Now if the system is non-LTI system, then in case of continuous time non-LTI systems, how you define the stability is you define zero input stability, that is in case of continuous time non-LTI systems, zero input response defines stability. It means what you have to do is, that is take your input x of t to be 0. Whatever relation you are given or whatever differential equation you have given, you just have to substitute input x of t to be 0 and then find the given by the given relation, then find the response yt. If y of t is finite, or you can say bounded, if y of t is bounded, then stable, otherwise unstable. If y of t is bounded, that is if you have taken 0 input and then you defined output, what you understand is there are two types of responses, that is 0 input response and 0 state response. That is, if you are talking about 0 input response, that is you have not applied any input, so the response must be due to the initial conditions that were existing in the system, because if you are not applying an input, then how the output is coming, there must be some initial conditions in the system. So if if the 0 input response will be bounded, then you will say that the system is bounded. And if you have taken input to be 0 and still the output is going to be increasing with time, and if it is going to be unbounded signal, then you will be saying that the system is a unstable system. So in case of continuous time system, we define like this. Now we are going to take one example on this, and we will be defining stability for non-LTI discrete time systems also. So whatever we have discussed, it must be a revision for you. You must have known all the things, but still sometimes if we are not revising the concepts, then we find randomly if some question is asked to you, then you can find some difficulty. So you must have to revise at times. So we are just performing that thing only, and now you are going to take the examples that you must have to solve. So be ready with pen and paper. We are just discussing one or two examples. Say for if you have to check stability of non-LTI discrete time system. In case of non-LTI continuous time system, how we define the stability? Taking 0 input response. But in this case, you have to consider output y of n to be causal. You have to take output y of n to be causal. It will be your first step, that is y of n is 0 for n less than 0. It means any value given to you as y of minus 2 or y of minus 1, all these values are going to be 0. You just have to take y of n to be causal, it means these values are 0. Second, apply a bounded input. That is, you can apply x of n. In most common, you can take x of n to be your step function u of n. In discrete time case, u of n unit step sequence. You have to assume output to be causal, and you have to apply a bounded input, that is u of n, in the system, and then observe whether output y of n is bounded or not. It will define the stability. What we have taken for a continuous time system, we have told that you just have to take 0 input, then see that whether the output for 0 input is going to be bounded or not. In case of discrete time, you will have to apply input but a bounded input, that is xn equals to un, and you have to take initial conditions, that is y of -2 or -1 to be 0, that is y of n is a causal signal. So these are the procedures, and see if we are going to take 2 examples on continuous and discrete time. So I am writing this, you don't have to wait for my solution, I will be solving simultaneously, but you just have to take the example and you should solve it by yourself only. So say we are given a differential equation that it is describing a LTI system. Say we are given in first case, say it is d2y of t upon dt square plus 6 dy of t upon dt and plus 8y of t equals to x of t. Let us say it is a differential equation that is defining a continuous time system. You have to comment on stability. Comment on stability. So you must be doing this question, and before I complete the solution, I expect that you will be completing the question, but due to the lag that is occurring, I am not waiting for your answer, I am trying to solve it now. So as we can see this differential equation, so first by the basics of systems, what you know that in this differential equation, we can see that all the coefficients are constant. It is 1, 6, 8 and 1. So if all the coefficients are constant, it means this differential equation is going to describe a LTI system, as here it is not like d2y dt square power 2 is not written. So this differential equation is going to define an LTI system. So this system is LTI. If this system is LTI, then we just have to follow the steps that we have to take the Laplace transform in it, and we know that if we say that y of t has a Laplace transform y of s, then by differentiation property you know that dn y of t upon dtn, that nth order derivative of this yt under 0 initial conditions, is going to give you s to the power n into y of s. So Laplace, if we are going to taking Laplace transform, so it will give you s square y of s plus 6 y of s and plus 8 y of s is equals to x of s. So if you take common y of s here, and if you get this ratio, that is y of s upon x of s, which is going to give you h of s, then it is going to be 1 upon s square plus 6s plus 8. So you have obtained the transfer function. Now you have to take inverse Laplace of this transfer function. So if you see, it can be written as 1 upon s plus 2 into s plus 4. So what you have to see here from this step, first you have to take the inverse Laplace. So if you will be taking the inverse Laplace, say this h of s is going to be a upon s plus 2 and plus b upon s plus 4. So coefficient values a, you can find it, a is equals to, you have to take the coefficient of 1 upon s plus 2, so it will be 1 upon s plus 4 at s is equals to minus 2, where this function is getting 0. So if you substitute minus 2, so it will be 1 upon 2. And if you take the value of b, that will be 1 upon s plus 2 at s is equals to minus 4. So it will be minus 1 upon minus 2, that is minus 1 upon 2. So this function is going to be a, that is 1 upon 2 e to the power minus 2t, and plus b into, that is minus 1 upon 2 into, it will be minus 1 upon 2 into e to the power minus 4t. So whenever you have not given any information about the causality of the system, then by default you have to take the causal inverse Laplace transform, as we have taken in this case. One more thing, if you are comfortable with the frequency response analysis, then you know that, or either in Routh-Edwards you also define this, that if the system poles are going to be in the right half of the S-plane for causal system, that system is definitely going to be unstable. But if you see here, if it is transfer function, then the poles are lying at minus 2 and minus 4. So if all the poles are lying in the left half of the S-plane, and if you are considering that the system is causal, then definitely the system is going to be stable. That can be verified from this, that if you have taken the impulse response that is inverse of this. So whenever you will be defining the impulse response, then all the coefficients of this transient term, you know that in this impulse response, first if you check whether this impulse response is going to be 0 at t tends to infinity or not, then if you check limit t tends to infinity h of t, then it will be, due to this negative sign in both the exponentials, all these exponentials are going to be 0, so the net value at t is equals to infinity will be 0. One more thing that you can recall from this concept, that whatever will be the coefficient of t in the transient part of the impulse response, it is going to be the location of poles. These are nothing but location of poles. These coefficients of exponential term will directly give you the location of poles. And if you see here, if the poles have real part that is negative as -2 or -4, it means the poles are lying in the left half of the S-plane, and if you have considering the system to be causal, so this system is stable, as this transient will be vanishing with t tends to with the increasing values of t, so you will say that this system is stable. So we have taken this example of a LTI system in case of continuous time, and you have defined the stability. So if I see here, it's stable, definitely. Priya, you have given this correct answer. Surjit, you have given correct answer. Manku, Palak, all the answers are correct. We are just defining that what can be two possibilities of the system that have to be generalized or analyzed for stability. So it is the first case, that is system is LTI. Now if we take a system, let's say we have given a relation that is -4 dy by dt plus 2y of t is equals to say x of t, or we say this dy by dt, okay, this -4, okay, whatever we have taken, we can analyze in any given case. I am not getting any particular example, I am not taking whatever is the example, we just have to check whether this is LTI system or not. So we have discussing in the concept of context of non-LTI system we have to take, so we can take this value to be -4. So we have taken now the coefficient of this differential equation to be a function of independent variable. So if you have to ask that whether this system is LTI or not, then you can say that as the coefficients of this differential equation are either constant or the function of independent variable, so this function, this system is linear but not time variant, not time invariant. As the coefficient is function of time, so the system is time variant, but the system is linear as this coefficient is function of independent variable. So this system is linear but time variant. So it is non-LTI system, it is a non-LTI system. So if you are going to define the stability of this system, then what you are going to take, you are defining zero input stability. You are going to define zero input stability, that is you are going to take input x of t to be 0. So if this input x of t is 0, this condition modified to t into dyt by dt minus 4yt is equals to 0. If you use the variable separable form of differential equation to solve this for y of t, then you can write t into, first you will be writing dyt upon dt is equals to 4 into y of t. So if we separate y of t terms on LHS and t terms on RHS, then you will be getting dy of t upon or 1 upon yt into dyt, we have taken this y of t as 1 upon yt, is equals to 4 into 1 upon t into dt. This dt upon this t came in the denominator. Now to solve this, we are integrating both sides with respect to t. If you are integrating this, then integration of 1 upon x dx is going to be ln of x. So it will be ln of y of t is equals to 4 times ln of t. We are not taking any constant. If you will be taking any constant and you will be defining that constant in terms of L log function, say you are taking here log c, then the result whatever will be coming will be the same. So we can left that. Now if ln of yt is equals to 4 ln of t, which can also be written as ln of t to the power 4. So if you want, then you can cancel this log term from both the sides and you will be getting yt is equals to t to the power 4. So what relation you are getting, now this output yt is dependent on time t with this value, that is t to the power 4. Yt is said to be bounded if it is bounded for every possible value of t, whether it is plus infinity or minus infinity as well. So if you are going to take t tends to infinity, then this y of t function will be infinity to the power 4, that is infinite. So you will say that this yt is not bounded, and as this output is not bounded, so this system is unstable. This system is unstable. So we have taken non-LTI continuous time signal, and one more example. If you have to find ZIR correct, what is the name? Anindya Bose. Yes, you are definitely going to use zero input criteria, zero input stability for non-LTI continuous time systems. This is the last example that I am going to solve, and then you will be starting the solutions. So take this example, that is, if there is a signal system defined by y of n plus 2 y of n minus 1 is equals to, I am not taking any new question, but just making you comfortable in the easy ones, so that when we will be taking the complex, then you can also solve or actually attempt that question. So if it is given like this, so due to this square term, whenever you see the square of any input or output in the relation, then it must represent a non-linear system. So if the system is non-linear, it means it is non-LTI system. And now if we have to comment on the stability of the system, then what you have to do is, assuming y of n to be causal, y of n to be causal, that is, you have to take y of n equals to 0 for n less than 0, and we can take x of n, any bounded input that we have taken, u of n. Now what is this, the shape of this function un, you know that this function is going to be started from n equals to 0, and it will contain same sample value, that is 1, from 0 to infinity. It will be 1, it is your function un, which is given, you are taking as x of n, it is having one value for any integer values of n from 0 to infinity. It means if you have to define u of 0, then it is going to be 1, that is, if the bracket term under this step function, if it is going to be greater than or equals to 0, then always the function will have a value, that is 1. If you have to define u of 5, then again this value is going to be 1 only. So now what you have to do is, you have to check this output yn. If you write this y of n output, then it can be written as x of n plus x square of n and minus 2y of n minus 1. You just have to find out values of this signal y of n for n greater than 0, as you have assumed that yn is 0 for n less than 0. So if you are taking y of 0, that is, if you want to find sample of this y of n at n equals to 0, then you are going to put n equals to 0 in the right hand side also. So it will give you, it is x of n, which is you have taken u of n. So you can write it here like u square of n, and you know that u square of n is nothing but un only. So in this part also you can write it to be u of n. It means you can define it to be un plus un. You can also take these two values to be 2u of n minus 2y of n minus 1. So if you want to define u of 0, then it will be 2 into u of 0 minus 2 into y of 0 minus 1, that is minus 1. Now as we have defined that yn is 0 for n less than 0, so this term, in this case, this y of minus 1 is 0. So it will be u of 0 is 1 into 2, that is 2. Now if you are going to take y of 1, then it will be 2 into u of 1 minus 2 into y of 0, 1 minus 1, that is 0. Again if you see, this value is 2 minus y of 0 is going to be 2, so 2 into 2, that is 2 minus 4, so it will be minus 2. Now if you take any value more than 1, that is 2, or y of 3 or y of 4, I am directly going to write the values y of 5, y of 6 and so on. So what we can see here, this term is always going to give you the 2 value, 2 into any value you are going to take is greater than 0, so this term is always going to be 2. So it will be 2 minus y of 2 into y of n minus 1. So if you see here, for n y of 2, 2 minus, if you put 2 n equals to 2 here, so it will be 2 minus 2y of 1, and as y of 1 is minus 2, so it will be 2 plus 4, that will be 6. Next value will be 2 minus 2y of 2, it will be 2 minus of 2 into 6, that is 12, so it will be minus 10. If you will be taking next value, then 2y of 3, it will be 2 minus 2 into minus 10, that is plus 20 plus 2, that is plus 22. Again y of 6 will be 2 minus y of 4, y of 5 will be, so it will be 22, 2 y of 4, 44, 2 minus 44, that is minus 42. So what you can see here, if we are going to plot the signal, then the first sample will be plus 2, next sample will be minus 2. From this point of time, the magnitude of next sample is always going to be increased, that is after 2 the next sample is 6, magnitude is greater than 2, after 6 it is minus 10, again the magnitude is going to be increased, again increasing, it means magnitude of y of n is increasing in bipolar direction, that is either in positive or in negative value, but the magnitude is increasing. So at n tends to infinity, y of n will have either plus or minus infinity value, so you can say that this system is non-stable, it is non-stable system. So we have defined basics of stability, and now you are going to attempt the questions. So please give some lectures on digital filters and system realization. Manku, only one demand. What should I do? I think I need your help. If you would be here, what you will be doing? I have told you that I have already given so many things for filters, but a few things that are still not yet covered, then it means that there is some restriction. We cannot deliver those things otherwise. Concepts are concepts, and what I have told you several times, that digital filters are never going to be any other things than a discrete time LTI system. So all the concepts are applicable, and we have also seen in the last video then how we realize the system, that is how we can represent the signal system in a block diagram representation. So realization part is a very easy you can say part, that you just have to make blocks. You have to take elementary blocks of filter realization, that can be delay elements or your transmittance or your signal multiplier or your constant multipliers. These are only 3 or 4 things that you are going to use for filter realization. So you can personally contact, if you are getting really so much trouble, then you can personally message me, and I can guide you whatever you will be facing the problems. I will try to minimize that. So just be ready. We are now taking small questions. So first question, please explain final value theorem of Z transform. So yes, Z transform, any topic we can discuss. For the time being now, we are going to take the questions. So are you ready? All of you are going to participate. How many of you are going to participate? I would like to see here. How many of you are going to participate in the questions that we are going to write here? Anindya Bose, Surjit Rabidas. Okay, I can see not so many names, but it doesn't matter. So first question that we are going to take is question number 1. You must have to answer with question number. So a system described by relation y of t is equals to d by dt of e to the power minus t x of t is, first A option is non-linear, B option is memoryless, C option unstable, and D option time invariant. So start answering the questions while I am writing some more questions. So you just try to solve these questions Question number 2 I am taking here. Which of the following is true? Which of the following statement is true? A option, a finite signal is always bounded, is always bounded. B option is a bounded signal always possess finite energy. Next option is a bounded signal is always zero. A bounded signal is always zero outside the interval minus t naught, it is given to be a closed interval for some t naught. And the D option is given to you as a bounded signal is always finite. So it is your second question, you just have to answer. If you know the answer, then it will hardly take 30 seconds to answer. Next question that we are going to take, it is question number 3. You just have to answer for linear time invariant systems, that are bounded input, bounded output stable, that are BIBO stable. If we have defined already, then which one of the following statement is true? Which one is true? A option is impulse response will be integrable but may not be absolutely integrable. Impulse response will be integrable but may not be absolutely integrable. B option is the unit impulse response will have finite support. The unit impulse response will have finite support. Next option is the unit step response will be absolutely integrable, And the last option is the unit step response will be bounded. The unit step response will be bounded. So these are four options for this question number 3. One more example I am going to take. Question number 4 we will be discussing here. You just have to solve the questions. You are now at question number 3 this time. We have defined PB linearity, Q be the time invariancy, R is causality and SB stability. So the system is given to you as y of n equals to x of n for n greater than or equals to minus 1, it is 0 for n equals to 0, and x of n plus 1 for n less than or equals to minus 1. So you just have to comment your answer as this system has the property P or Q, or you have to write PQR, something, whatever are the properties contained by the system, you just have to comment y of n equals to this. One more example I am giving you, say question number 5, that y of n is given to be, it is x of n minus x of n minus 1, and this is for minus infinity to minus 1, and it is n into x of n otherwise. X of n minus x of n minus 1, it is given for n in between minus infinity and minus 1, and this relation is given y of n equals to n into x of n otherwise. So you just have to comment on stable or not, stable or not. So I hope you must have solved at least 2 or 3 questions. I can see your comments. So to see your comments that are not visible now, I will have to check my YouTube. So answers are Shubham, first answer Pallav Anand, we have from Pallav. Then we can make a table. Question number 5 we have taken 1, 2, 3, 4 and 5. Now I am writing the names Pallav, then Shubham. Now I am writing the names. Then Vinu. Meanwhile, you just solve the questions, question number 4 or 5. Vinu, Priya is participating. Next, Anindya. Good, we have more names. Surjit, Rabidas. Then, okay, so till now what I can see, Pallav Anand, question 1 unstable. Means first you have given option C. Then Shubham Gupta, first C. Next, Priya Verma, first non-linear A. Next, Anand, first unstable, that is C. Surjit Rabidas, sir, second. Nota ho sakta hai, not applicable. No, it cannot be nota. You must have to select from any one of the given options. Then for question 2, Vinu, question you have given for question number 2, you have given D. 1, 2, 3, 4 and 5. So we just want to check how many of you are participating and are getting correct answer, because whatever we are going to deal is, we have just discussed the things. So at least 2 or 3 questions you must have to able to answer. Priya, question 2A, okay. Next, Anindya 2D, Anindya 2D. Next, Pallav 2D, 2D. Next, Anindya 3B, okay, 3B. We have, I think we have these much answers till yet, okay. So how many of you are going to attempt? Okay, some more responses. Option 2, Yogita Verma. Okay, Yogita. That is, you are writing question 2, option A. Okay, it is option A. Next, Vinu, 4P and S. Vinu, 4P and S. Next, Manku, 1C, 2A. Okay, again it is Manku, 1C, 2A. Okay. Vinu, Manku, Shubham, 4PS. Shubham, 4P and S. More options? Have I missed something? Shubham Gupta, 5 unstable. Shubham, 5 unstable. Okay. So now have you attempted all 5 questions? Should I start to see the solution, to discuss the solution? Surjit, 1A, 2B. Surjit 1A and 2B. Okay. Pallav, question number 4, P and S. P and S. Okay. Abhishek Chauhan. Okay. Abhishek, I can't find your responses. Where are your responses? Veenu Hirani, 5 stable. 5 you have written stable. Oh, unstable it is? Unstable. Okay. Unstable. So now we are going to discuss these examples. First, if you see here, whenever you have a differentiator, say you have a response simply given to you as y of t is equals to d by dt of x of t. Whatever you have seen, that if we are going to take any bounded input, then this response must be bounded. So if we take x of t equals to ut, then for x of t equals to ut, if you substitute x of t to be ut, or we can write d by dt of ut, then you know that differentiation of step is going to give you an impulse, which is not bounded. It is unbounded signal. It is unbounded signal. So if you are applying a finite input, bounded input, and you are getting an unbounded output, therefore this system is not stable. Similarly, if you are taking an integrator, that is, if y of t is going to be integration from minus infinity to t x of tau d tau, then again if you are taking x of t to be ut, then integration from minus infinity to infinity step function will give you a ramp function, and that ramp function is going to be infinite. Therefore, at t tends to infinity, so this output is again going to be unbounded. So whether the system is described by the differentiation of input or by running integration of input, both of these systems are not going to be stable. That means both of the systems are unstable. Now if you see the given case, if it is given to be yt is equals to d by dt of this, so you can use the property of multiplication, differentiation of multiplied functions. That is, first if you take e to the power minus t common, and then you have to differentiate x of t. Say we are taking x of t to be ut. So differentiation of x of t will give you del of t. Next you will take x of t, that is ut constant, and if you will be differentiating this function, then it will be minus of e to the power minus t. I can merge that minus sign with here. So now this term is going to be finite. If you see e to the power minus t ut, then it will be a decaying exponential for positive values of t. But if you see this term, it is the product of any function with impulse function, and you know that x of t into del of t is going to be x of 0, that is value of this function at t equals to 0 into del of t, and this function will be e to the power minus t u of t. So now if you see value of e to the power minus t at t equals to 0, it is going to be 1, so it will be del of t minus e to the power minus t ut. This function is going to be 0 at t tends to minus infinity, but this function is infinite, which is existing at t equals to 0. As this function is not bounded, as this part of the output is unbounded, so we can say that overall output is unbounded, and therefore this system is what? Unstable. So this system is unstable. So first option C is correct, Pallav correct, Shubham correct, Priya correct, Anindya correct. Sorry, it is, if you have written option A, then you will have to check. Otherwise, Anindya, you have given the correct option. So these options were correct. So what you have just to understand, that whenever there is a d by dt of x of t expression, it means it is going to be unstable, but it will be linear, right? If there will be d by dt of x square of t, then it will be non-linear. And if you are going to get running integration, that is yt integration minus infinity to t x of tau d tau, if any of the limits of integration is infinite, then the system is going to be unstable. But if you are taking the integration only between some finite limits, then the system will be stable. So this point must be taken care of, that if any of the limit is either plus infinity or minus infinity, then this relation will represent an unstable system. Otherwise, if both these limits are finite and you are taking the integration of any bounded input, then you are going to get the bounded result. In that case, yt represent this system will be stable system. So we have taken this first question. Now we have taken this second question because there may be some confusion with these type of words. A finite signal. What is a finite signal? And in the next question, what we are getting, response will have finite support. So what is a finite signal and what is finite support? These are two different things, and bounded is the third thing. It means you must have to take care of three words. Bounded is different word, finite support is different word, and finite signal is different word. So whenever you see bounded, you say bounded, you have just seen that if the maximum value attained by the signal is going to be finite, then you say that this system is bounded, that signal is bounded. So if you are taking a ut function, say x of t is equals to 4 ut, then this u of t function is what? It is bounded. And a finite signal, if you use the word finite, then that finite means the coefficient of this function. That is, if you are going to define a function that is aut, then this part is bounded. But this coefficient defines whether the signal is finite or not. Finite or not will be defined by this amplitude, that is the coefficient. In case of unit step function, it is amplitude. In case of ramp, it is slope. In case of impulse, it is area. So whatever is the constant of coefficient of bounded signal will define that it is finite or not. So now if you see the options, a finite signal is always bounded. Say you are writing a function that is x of t is equals to 4 r of t. You know the function r of t is going to be linearly increase, and if you are taking 4, that means the slope of this ramp function is 4. So if you are representing a ramp which has slope value 4, then it will give you 4 rt, that may be written as 4t ut, and it will be at t is equals to 1 seconds, you will be having 4, at t is equals to 2 seconds, the value will be 8, and so on, so that you can say that the slope of this ramp function is 4. So now in this case you can see you can say that coefficient of this r of t is finite, but this r of t will have infinity value at t tends to infinity. So this function cannot be said to be a bounded function. That is, a finite signal can or cannot be a bounded signal. So this option A is not correct. A finite signal is always bounded. It is not correct. A finite signal may be unbounded. Next, if you see, a bounded signal always possesses finite energy. Whenever you talk about energy and power, then you have seen that all the periodic signals are mostly periodic signals are power signals. There are some you can say illustration like tan x either, or you can say periodic impulse train. These are periodic but not power signals. But if the signal is periodic, then either it will be power signal or it will be neither energy nor power signal. So if you take any periodic signal in case of sine or cos, if you are taking a sine function, then if you see, if you are defining sine t with respect to t, then this function will have amplitude 1, that is, it will be excursiong in between -1 and +1. So if you have to define bounded or unbounded nature of this signal, then you can definitely say that this signal is a bounded signal, as it has the values only in between +1 and -1, which is never going to be infinity. Therefore this signal is bounded. But you know that energy of any periodic signal is what? Infinite. It means this signal is a power signal. It is a bounded power signal for which energy is what? Infinite. So the statement that is written in the option B, that is, a bounded signal always possesses finite energy, it is again wrong, as if the signal is either periodic or there can be some certain different conditions in which a bounded signal can possess infinite energy. So this option is again wrong. Next, if you see, a signal is always 0 outside the interval -t0 and t0 for some t0. It means it is trying to say that a bounded signal, a signal is always 0 outside the interval for some t0. A signal is always 0 outside the interval this for some t0. See, it may be possible that I have missed some word of this option, otherwise meaning is, I think, not getting very clear. A bounded signal, okay, here it is a bounded signal. So it must be MTA, that is marks for all. That's why some of you have asked that can this question go to nota or not. Definitely. So it is the statement like a bounded signal is always 0. See here, it is not necessary that the bounded signal will be existing only between two finite limits. A bounded signal can exist in infinity duration. Like if you say, if you are taking this signal, that is e to the power minus t ut, then if you see, this function is going to have maximum value, that is 1, and with respect to t, if you are going to increase t in positive direction, then the value is going to be decrease. So this signal is bounded, but it is existing in infinite duration. So the C option, that is a signal that is bounded, it must be 0 outside this interval. This statement is no way true. So again you are now just left with one answer, that is a bounded signal is always finite. It means bounded signal, value of the bounded signal is always going to be finite. That's why you can say that the signal is bounded. If any of the value in the signal will be infinite, then you cannot say that the signal is bounded. So if you have told that the signal is bounded, then a bounded signal is always finite. So this option D is correct for question number 2. Now before checking the options that you have given, first we see one more term, that is finite support. If you are taking the word finite support for any function, actually it is this term particularly used more in mathematics when you define any function. Say you are defining x of x, let it is any function, then this function is said to have finite support if this follows whatever relation it is written here, let it is written x square plus 2. Then if this relation is true only for some finite values of x, that is this function is going to take only some finite value of x, if then this relation is true, then you say that this signal has finite support. It means you can say that if the signal is a discrete time signal and if it is existing in a finite duration, then it will have finite number of samples, that is signal will be defined only for finite number of values of n, then you can say that this signal is a finite support signal. So now if you see here in this question what we have given for LTI systems, first thing we already have given that the systems are LTI, that we are going to discuss. Next, that are bounded input bounded output stable. It is again told that the system is known to be LTI and BIBO stable. Then we have to check which of the following is true. First statement is impulse response will be integrable but may not be absolutely integrable. These are some options what I taught you, that there must be some option in GATE exam which will be forcing you to think that have we missed some concept. It can be assumed by some students that yes, we have learned that impulse response should be integrable. But what I have told you, impulse response must be, we have used the term absolutely integrable only. We have never said that impulse response will be integrable. This word we have never used. What word we have used? Impulse response must be what? Absolutely integrable. So this option is definitely not correct. Impulse response must be absolutely integrable in every condition. Then only you are going to say that system is stable system. Next, the unit impulse response will have finite support. Again, it means that unit impulse response exists only at finite instants of time. That is, again if you are going to take a discrete time signal, that is unit impulse response if you are taking, and if it is having infinite samples, but if the shape is exponentially decreasing, say it is your impulse response h of n with respect to n, then if the signal is not having finite support, that is if it is defined for infinite number of values of this x-axis, then also the impulse response can be absolutely integrable in case of continuous time, or in discrete time we define summation from n equals to minus infinity to infinity mod of x of n. This value must be less than infinity, then you say that the impulse response is absolutely summable. So if impulse response is having finite support or it is having infinite support, it can represent stable system. So this option that the unit impulse response will have finite support, it cannot be taken as a generalized statement. It cannot be valid for each and every system. It is not possible that it is valid for each stable system. So second option is again you are going to eliminate. Third option, if you see, the unit step response will be absolutely integrable. For stability, we have confined to integrability of impulse response. What we have defined that only the impulse response must be absolutely integrable. We have never told that unit step response or parabolic response. What do you mean by unit step response? If you are going to apply a unit step signal in input, then the response obtained is called to be a unit step response. So if a system is stable, then its impulse response must be absolutely integrable. This criteria is not applied on any other input other than impulse. That is, this statement that the unit step response will be absolutely integrable, it is not correct. Now if you see the last statement, if you have not read any of the statements and if you have just read the fourth statement, what the statement is? the unit step response will be bounded. What is this unit step response means? Response for unit step input, that is, you are going to take input x of t for the system to be step function ut, which is what? A bounded input. If you are taking step function as input, it means you are applying a bounded input in a system which is LTI and bounded input, bounded output stable. So if this system is bounded output, bounded output stable system, then response for step function is definitely going to be bounded. Response is definitely going to be bounded, but it is not necessary that this response will be absolutely integrable. So obviously this option is correct for this question. Next, if you see the two more question, now can I read some of your statements? Shubham, yes sir, I was saying yes, definitely, it's my mistake. I have missed this word bounded, therefore this question will definitely go to a MTA. Question number 4, option P. Yogita, I can see question number 4, option P, and some more options I have missed. Taksh Patel, is it useful for electrical? Definitely it is useful, and you can say it is more useful for you. Venu, yes, okay. So now what we can see here, option 2, for option question number 2, it is D. Almost all of you have given D, but if you are either given A or given B or given C, still I am taking all of these options to be correct, and all these options are giving you the marks. Next, if we see question number 3, what we have obtained is, for question number 3, it is the most easy question out of all of these 5 questions. What you just have to do is, you just, if you have read the D option, and just understand that what this option means. If you are ever going to get the word either parabolic response, it means you are going to apply input a parabolic function, then the response is said to be parabolic response. So if it is given unit step response, means you are taking a bounded input, that is ut, and if the input is bounded and system is BIBO stable, then definitely that response will be bounded. So this option D is correct. So I am really sorry that this option 3 I am not getting answers, and no correct answer is there. It is really not good to see, but still I hope now in the future, if there will be some question related to these two concepts, I hope you will be solving those questions. So what is the difference between periodic and circular? See, we have concluded, we have uploaded the lectures on circular and periodic convolution as well. You can go through, I think, question number 8 or 9 or 10 of 10 challenging questions. You will be getting the concepts related to all the convolution, that is either linear convolution or circular convolution or periodic convolution. So now we are going to check this question. P is linearity, Q is time invariancy, R is causality, and S is stability. So first we see, if we are taking this relation causality, then from this relation you have defined that y of n is going to follow one of these relations depending on the values of n. So whatever value if you take, if you are having any term like this, x of n plus 1 or n plus something, whenever there will be a term x of n plus something, definitely this system is not going to be the causal system. As say you have to find, it is valid for what? For n less than or equals to minus 1. That is, if you want to find y of minus 2, which is less than minus 1, so this relation will be applied. So y of n, that is y of minus 2, will be given by this relation, that is x of, you have taken n to be minus 2, so it will be minus 2 plus 1, that is what? X of minus 1. With respect to minus 2, minus 1 is future input. You are trying to check output at n equals to minus 2, and to define this output you need to know the value of x of minus 1, which is going to come after minus 2. It means present output depends on future outputs, so this is not true. System is not a causal system. So R cannot be there. Next, if we see, we have discussed linearity. If you have seen the lectures on linearity, then we have discussed that if the system is splitted in time, that is, if this splitted in time for n less than or equals to any values are defined, then systems splitted in time is definitely going to be stable. Here it is not any, it is the coefficient of these terms are either 1 or 0, 1. In this relation, if the coefficient would be function of time also or any independent variable also, let it is written n into xn, n square plus n into xn, still this system will be linear. If there will be coefficients also, and if it is splitted in time, then the system is definitely going to be linear. What not be the term for linearity? There must not be x square of n. There must not be 1 upon x of n. Any power other than 1 of x of n must not be there, and if it is splitted in time, then it will represent a linear system. So this system is definitely going to be what? Linear. This system is linear system. Again, if you check for time invariancy, we have seen that if it is splitted in n, then it will be linear but not time invariant, because if you are going to find y of n minus n naught, then you are going to replace all the n's by n minus n naught in the first case, and when you are going to get the response of the system for delayed input, then you don't have to replace all n's by n minus n naught, but you just have to take, in this input you have to take n minus n naught. So both two things will not be same, as in one case you will be defining this n minus n naught to be minus 1, and in the next case you will be defining n must be greater than minus 1. So this system is definitely not a time invariant system. If it would be written like x of n all the places, if it would be written like this, then this system will be time invariant system. We have seen that if this splitting is done for values of x of n, then the system will be time invariant but not linear. But if it is given for n, in this case, then this system is time variant but linear. So this difference must be taken care. That's why I have given this example. So this system is not time invariant. This system is not time invariant. Now if you check the stability, so either of this relation, if you see, say if you are going to analyze for n greater than or equals to minus 1, then the relation is what? Y of n is equals to x of n. If you are going to check at n equals to 0, then what is the value? Y of n equals to 0. And if you are checked for n less than minus 1, then what will be the result? Y of n equals to x of n plus 1. In both the cases, you can see here, if x of n is bounded, then definitely this will be bounded. If x of n is bounded or unbounded, this will be bounded as it is given to be constant 0. And if x of n is bounded, then x of n plus 1 must be bounded. Therefore, this also will be a bounded output. Therefore, in all the cases, that is splitted in time for 3 cases, for all 3 cases you are obtaining that if you will be applying a bounded input in the system, then the response in all 3 cases are going to be bounded. Therefore, this system is a stable system. It means this stability condition is satisfied. So the system is P and S. I have seen some of you have given the option correctly, that is this system is having properties P and S. Now if you see the fifth question, y of n is again splitted in time. So we have just to comment on stability of the system. So how you can comment on stability? Here it is, x of n minus x of n minus 1. Whenever you are going to get a bounded input, you just have to check for both the condition, that in either of the condition, if you are going to get this output yn to be unbounded for bounded input, then the system will be unstable. So you must have to check individually for both the relations. Say the first relation you are going to follow, yn is equals to xn minus 1. So if you are applying a bounded input, then xn is finite and x of n minus 1 will definitely also be the finite. So finite minus finite is always going to give you a finite value. So if this relation is taken, yn equals to xn minus x of n minus 1, whatever is the range of n we are not considering. So if the output is following this relation, then the system is stable. Then the system is going to be stable, as difference of finite values will give you the finite value. So the output is bounded and we can say the system is stable. But now if you see the second relation, the next relation you have given is yn is equals to n into x of n. Now this relation is going to be followed otherwise. What does it mean by otherwise? From minus infinity to minus 1, you have to follow this relation, and otherwise means you have to follow this relation from n in between 0 and infinity. That means you will have to take value of n to be infinity also. And for the system to be bounded input, bounded output stable, this output must be finite even at n equals to infinity. But if you see here, n is used as a coefficient of input. So if you are applying a bounded input, still as the coefficient may be infinite of that bounded, say x of t is 1, x of n is 1, but infinity into 1 will give you infinity. Therefore, this system will represent will represent a unstable system, because n is in coefficient and this n can be vary from 0 to infinity. So this system will have infinity value of response at n tends to infinity, therefore this system is unstable. Now if I reverse the condition and if I write that I have just made one change in this relation and we have written that for n 0 to 10, if we have defined n to be finite only, if this n is now going to vary in between 0 to 10 only, if this limit is going to be 0 to 10, then you can see that if this x of n is bounded, that is if it is finite and you are now multiplying with finite n, then the system will represent a stable system. If the limit would be only finite for this n, then this system will be stable, but as we have given the limit to be otherwise, as here written otherwise, it means n can be 0 to infinity. If n can be 0 to infinity, in this case the system is unstable. So we have discussed these 5 questions. Now we can take some more questions, but I would like to check. Shubham has given the correct option, Pallav has given the correct option. Only 2 options, I think. Anand Bose, also I can see your option. So Anand, you have also given P and S. So, and also Veenu have also given. So these 4 options are correct. Now what we have done with these 5 questions. So are you interested? Do you want to solve some more questions? Then we will be taking some other questions on these concepts. Stability is very important. You just have to keep practicing on stability. So I am just making space, and if you will be comfortable and if you will be interested, then we can take some more questions. So one more thing that students get confused, that one thing we have discussed, that unit step response must be bounded, but unit step response must be absolutely integrable. It is not correct. It means unit step response, if it is if you have to check the stability by the unit step response, then this unit step response must be bounded but not absolutely integrable. One more thing, that say we have a relation that is given to you as, just comment for this, we are just taking as at a question only, but we just have to discuss some concepts, that if it is given to be ramp function r of x of t, if y of t is r of x of t, then say this system is stable or not. Comment that it is going to be stable or not. Sir, what is the center of gravity of a signal? See, it is not defined in the syllabus of signals and system as I have ever seen, that center of gravity of a signal. But in a particular case, it can be given to you that this given signal defines a center of gravity. In basic mechanics, you must have read center of gravity, moment of inertia. But if you are finding this word center of gravity in your signal syllabus, then it was related and it was already be defined to you that what is the center of gravity. It has just named to you to be center of gravity. So you just don't have to do anything with that word. You just have to find out the other thing that is specified in the question. Just don't get confused whenever you find such words in signals and system. You just have to work smartly and to decide that there is nothing to do of this word with signals and system, and you can definitely solve that question without using the concept of this. The concept must be defined in the question itself. So yes sir, interested Viru. Anand Bose unstable, John Paul stable, Manku unstable, John Paul stable, Pallav unstable, Afroz unstable, Shubham Gupta stable, Surjit Rabida stable, Priya Verma unstable. So see, we are taking easy questions. These are easy questions, but it can confuse you. And if you are getting confused in this question, then there can be a question in GATE in which it will be a part of that question. What we have taken, we have just seen here that the impulse response stability unit step response must be bounded, but it is not necessary that it will be absolutely integrable. Similarly, Yogita Verma stable, DS Pone, sir please clear my doubt. Actually the doubt is not visible on the screen now. Okay, so you have retracted your message. So if we want to check this concept again, you just have to be very sure and very clear what is going to be the BIBO stability. BIBO stability states I am again writing it that output must be finite for what? Finite at any instant of time. Any instant of time. That is for minus infinity to t plus infinity, or n from minus infinity to plus infinity if we are taking y of n, yt, or we are taking y of n. Then bounded input, bounded output means if you are applying a bounded input, it must be finite for what? If input is bounded, if x of t is what? Bounded. And when you say this x of t to be bounded, when it has never reached infinite value, it means if all the values contained in the signal x of t is finite, then only you are going to say that this signal is going to be bounded. So if you want to plot y of r of t, by the definition, you know that r of t is going to be t into ut, right? So if you are going to replace this t by x of t, what you have to find out? R of x of t. So it will be x of t into u of what? X of t. You have just replaced all t by x of t. So you know that u of x of t, what does this function means? Again, you know that ut is going to be 1 for t greater than 0, and it will be 0 for t less than 0. It means if you are writing u of x of t, then this function will be 1 if bracket term x of t is greater than 0, and it will be 0 if x of t is less than 0, right? So if you see here, u of x of t, this term will be 1 only if x of t is greater than 0. So if you will be plotting the function, then your now you can plot this function to be, this will be your x-axis, that is not t now. If you are plotting r of t, then your argument is t. Now you are plotting r of x of t, it means in x-axis you have x of t, and you have to plot x of t only for x of t greater than 0. This is the reason in which x of t is less than 0. So you will be having this function r of x of t will be 0 for left half of this plane, that is this point is x of t equals to 0. This point is what? X of t equals to 0. So below this point, before this point where x of t is less than 0, this r of x of t is going to be 0, so it is 0. Now after x of t equals to 0, function is going to follow r of x of t will be x of t itself, because in this region this function is 1, so x of t into 1 is what? X of t. So we have just to plot x of t for t positive, x of t positive. Therefore you will be getting nothing but a ramp function, but not respect to time, with respect to x of t. It means if you see here, as if you are writing r of t is equals to t ut, as you are writing r of t, that is t ut, then this function will be infinite, where this function is going to be infinite only at, if you are going to define the value. It is correct that ramp function is linearly increasing, but if you will be trying to find value of this ramp function at x of t is equals to 1 lakhs, then you will be getting the value to be 1 lakhs only, as this function is having slope 1. Therefore you have written x of t on both the axes. For x of t greater than 0 you are plotting. So what you can see that the slope of this ramp is 1, that is if x of t is 1, then here also you will be having the value 1. It means as r of t is infinity only at t is equals to infinity, similarly you can say r of x of t will be infinite only if only at x of t is infinite. When you are going to take this x-axis to be infinite, then only this y-axis value will be going to be infinite. But now what you have defined here, that you defined BIBO stability only for bounded inputs, and for bounded inputs this x of t is never infinite. It is never infinite, it is always finite. Therefore you have defined this to be a bounded input. So if this x of t is bounded and you have taken r of x of t, this function can be infinity, but only at when x of t is infinity, and if this condition is excluded, that it means then r of t is always going to be finite, is finite if x of t is not equals to infinity. As we have taken that it can never be infinity if it is a bounded signal, so r of x of t will always have a finite value. It will be finite only at x of t is infinite, but as x of t is never going to be infinite, therefore this function will also be finite, and therefore you can say that this system represents a stable system. This system is a stable system. So these are very basic things, but you must have to stick with your basic concepts. It is the concepts only that yt must be finite for finite input. We cannot define that if yt is infinite for infinite input, then it will be a stable, it will be an unstable system. We cannot say that. So, sir, clear my doubt. If I have applied unbounded input, we get bounded output. I have just told we have defined the bounded input, bounded output stability. So you cannot deal with unbounded input. You cannot take any unbounded input. If there is a signal system that is producing bounded output for unbounded input, then we have seen that. We have seen that, let's say it is a system which is having the relation, which is represented by this relation y of t is equals to e to the power minus of mod of x of t. So in this case, it is a system which will be having bounded in output even if we are applying unbounded input. But what I am trying to say, you just skip this thing, that why you want to apply unbounded signal to check stability. You just don't have to apply any unbounded signal to check stability. But you must have to be careful that if you are saying that a system is bounded input, bounded output stable, then it must produce bounded inputs, bounded outputs for every bounded input. Say we have one more example. All the examples that I have taken today, these all questions are from previous year GATE. So I expect that you must answer these questions. If you are preparing for GATE, then it is the first tool, it is the first requirement that you must have very clear understanding of all the previous questions. So if you have not attempted yet from 90 to present of all three branches, if you are a student of electronics branch, then it is not like you just have to do previous year questions of electronics. If you are studying signal, and if signal is also in EE or IN, then you must have to complete all the previous questions from these two branches also. So say we have a system which is defined as integration from minus infinity to t x of tau into cos 3 tau d tau. Now you can see here, if you will be taking, if you have to define the stability, so it is again a question of GATE. I am not sure about the limit, but we will be performing what I will be analyzing for this limit, that if it is given that from minus infinity to t x of tau cos of 3 tau d tau, then this system stable or not? LS Manku, finite support means finite duration. Yes, you can almost say that. I have told you that a signal x of x is going to be the finite, it is going to have finite support if the relation that you are using is valid for finite values of this x only. Then this signal is said to be have finite support. And John Paul unstable, Shubham Makar unstable, Anindya Bose stable. Again you are having two options, stable and unstable, but it's good, nothing wrong with it. We are just defining the concepts and we are just practicing. Arpit Verma stable, so 50% options are unstable and 50% are stable. Now stable is having more percentage, as Surjit Ravidas has also said to be this signal to be stable. Pallavanand stable. So now LS Manku stable. Most of you students are giving stable, and then Palak Gaur has given unstable, Sashank Saurav has given stable. So these are not the questions that I was planned to give you, but still we are taking these questions only. Questions are just the medium to practice and to gain some concepts that may be missing or may be confusing you. So we are just taking random questions. If yes, John Paul has got the point. So now we can discuss this, that whatever what we are discussing, that if you are saying that a particular system is bounded input, bounded output stable, it means it is not like that. If for any it must produce stable output or bounded output for every bounded input. Like say if we are taking case 1, if we have applied input x of t to be a bounded signal, that is u of t, then what this relation is giving you, y of t is equals to integration from minus infinity to t u of tau into cos 3 tau d tau. Now if you see here, you are integrating with respect to tau, and this u tau function, you know that it is going to be 1 only for t greater than 0. So if you want, then you can take value of this signal to be 1, therefore we can take one value for this signal and we can change the limit. Instead of minus infinity we have written 0 to t, because before 0 the function is having 0 value u of tau, and for 0 to t it is going to have value plus 1. So now you are going to integrate this cos 3 tau, which is having a shape like this, it is going to have shape like this, and if you are going to integrate this cos function which is having finite, or you can say 0 area in one time period. So if you are going to take finite time interval, if you are going to say you are going to take this value, this time to be t, and you are going to integrate this, that you are going to find area under this function from time t is equals to 0 to t seconds, then we have discussed that is, if this limit is what, if it is finite, then definitely this is going to give you the finite result, it will be finite, and you can say that for ut, which is a bounded input, the system the system is producing bounded output. Bounded output. So in first case, if you have taken your input to be ut, then this system is producing finite output, therefore most of you have given the option that the system is stable. But what we have discussed is, if it is a bounded input bounded output stable, then not only for ut but for every bounded input this output must be bounded. Again, if you see, whenever there is a sinusoidal term, that is sine or cos, then what you just have to do is check this for the same signal as input. That is, if you are taking x of t to be cos 3t, again if you are going to define cos 3t, then it is going to be a bounded signal, as amplitude of the signal is 1. So it is again a bounded signal. In this case, yt can be represented as y of t will be integration from minus infinity to infinity. If x of t is cos 3t, then x of tau will be cos 3 tau. That is, cos 3 tau you just have to, x of tau you have to write here. So it will be cos 3 tau into cos 3 tau d tau. Cos 3 tau into cos 3 tau can be written as minus infinity to t cos square 3 tau. And this cos square 3 tau can be written as minus infinity to t 1 plus cos 2 theta. Cos square theta is 1 plus cos 2 theta divided by 2. That is 1 plus cos 6t divided by 2 dt. So now if you are going to integrate this, then you can integrate it in parts, that is integration from minus infinity to t 1 by 2 and plus integration from minus infinity to t cos 6t, or it is actually tau, with respect to tau we are taking. So it is tau, it is again d tau, and it is 6 tau d tau. So now if you see here, if you will be integrating 1 by 2, then the result will be 1 by 2 tau, and now you are going to take a limit that is minus infinity. So when you will be taking the limit, that is lower limit minus infinity, so due to this minus infinity limit, you will be taking an infinite term in this response. That is, the input that you have taken, it was again a bounded input, but for this bounded input, the output that you are getting will contain infinity, that is, this output is going to be unbounded for a bounded input, therefore this system is definitely not a bounded input bounded output stable. So whenever you are getting cos 3 tau in like terms, then you just have to take input to be the same sinusoidal function, then you will see that this function is not going to be a stable system. But what we have already discussed and what I expect from you, I have told you that irrespective of this term, if you are going to integrate x of t, and if there is any one of the limit to be plus infinity or minus infinity, then you just can say that this system is never going to be stable, it will be a unstable system. So I think now you can recall these concepts. So it's almost 4:15. So we are concluding today's discussion. We have taken stability in time domain. We have discussed some of the examples. So wherever if you have mistaken, if you have committed any mistake of any of the questions that we have taken, so just keep in mind either that thing or note down at any place and Similarly, that now you will be performing your test also in test series. So whenever you are getting any some error, that if you think that you are good in these concepts, but still if the question is not converting and not giving you marks, then these are the first area where you have to improve. You just have to improve your strengths first. Then you have to see what are your limitations, what are your you can say what concepts are missing. Then you have to follow those concepts. But whatever concepts you are having, you must be very sound in that concepts. So I think we have discussed enough on stability of system in continuous time. System realization, one video. Okay, Zaid, we will try. System realization is a basic thing, and I think you can get lectures on system realization on different channels. It is not a so vast thing that you will be waiting for me to cover. You just have to complete from anywhere else, and you can post the doubts on system realization. If you are having any doubt, then please post it on Telegram, and it will be better if I am not replying you, then if you send it to me personally, then it is more chance that I will be replying it fast. So thank you so much. I have enjoyed this session, and I will be planning some more sessions that will be containing the concepts that are frequently asked in GATE. We have to cover the frequently asked concepts in GATE first, then we will be seeing what are missing. So thank you so much for your support, and thank you so much. All the best. Keep practicing. Thank you.